So welcome to the presentation 9 of this algebraic structures course that I'm teaching online. And the book that we are using is Abstract Algebra, Theory and Applications by Thomas Judson. You can just go to Google and you shall find that PDF copy is free at this time. Okay, so today we are going to look at just one special kind of a group, okay? And the group is going to be defined in the following manner, that let X be a non-empty subset, all right? Okay, so X is a non-empty subset, and then, okay, and we are looking at rather G equals the set of all 1 onto maps, okay, or all say bijective maps from G to G, okay, then actually from X to X rather, I'm so sorry. So now we are going to get, really lots of symbols in here, X to X. So then what will happen is that we are going to show that G is a group, okay? So G is a group, and to show that G is a group, all that we have to do is verify that, look at the associativity. So we know composition of maps is associative. So that works. Then we have to show closure. But we have seen, I think in the very first or the second presentation, or in the first chapter of the book, that composition of two bijective maps is bijective. So what does that show? That we have closure in G. That is, if I take two bijective maps from X to X, their composition is also a bijection, and I did not mention it here. I don't remember I did. The operation is the composition of maps. I mean, by that, this time, I don't know why I am rushing again. Let me not do that. Okay. Now, you know this, that if I define a map I from X to X, okay, by I X equals X for all X in X, then this, if I compose this function with any other function, it leaves the function unchanged, right? So or in other words, what we have is that I composed with F is F, right? That is, it doesn't really, and is F, and so is FOI. Now we have seen that in case this is going to be a group, or when we have associative property, just one side is enough. Okay, so for all F in G, right? Okay, and then you know this here, that for any, if F is a bijection, or 1 onto is a bijection, then F inverse, for a bijection, we have an inverse map, okay? So F inverse exists and is also a bijection, and is a bijection. So you can see that G is a group, all right, with composition of maps as binary operation, okay? And this will be a non-abelian group, you can see, and as an example, you can verify that if you take, say, uh, X to be the set of real numbers. The, and I define my G to be this, that G consists of maps from say R to R. So let me just write it like this. That is consists of F, and let me just put something in here, say F sub alpha, where F sub alpha is a map from R to R, okay, R to R, and let me change this to English because there are too many symbols for no reason, such that, okay, all right, and we are defining fx to be, okay, alpha x, where x is a real number, all right, and alpha is a non-zero real number, okay, so alpha x, and then x is real, or x and alpha are real numbers, okay, so x and alpha, they are in R, okay, or they belong to R in other words, okay, and alpha is not equal to 0. Now I'm not going to really, flood you with my lecture by going over the verification of this. I'll let you do it at your own leisure, okay? So, and alpha is not equal to 0, okay? And let's correct this. All right, so let's just go to the cases that we are going to work on in this presentation, okay? So now for the remainder of this presentation, as I said, we are going to focus our attention on the bijections on a set, okay, that are finite, okay. And what we will do is this, that is, we will first look at our sets as finite sets, say it has n elements, then we'll just number them from 1 through n, all right, and later when necessary, we will use other symbols, okay. So set of size 1, or a set with only one elements. So say we are taking that, all right. So we have set of only one element. So what we decided to do is we decided to call it 1. So in this case, how many elements will G have? G will have only one element. And let's just get one more notation, okay? That is in the here, we shall now express our maps by this type of a bracket. On the top, we will write the element in the domain, and in the bottom, we will write the element that it is assigned to. So in this case, we have only one element, that is identity, and you can see that that forms a group, okay, because inverse of the identity element is identity, composition of maps is closed and is associative, okay, so everything is good, okay. So let's look at a set of size 2. Don't think that I'll be going over all different sizes the way I went over the unitary groups in the last one. I would not do that to you. Maximum I would go probably is 4 for discussion in detail, okay, but no more than that, okay. So here, so now what happens is this, in here, first of all, I'll have to have room for one more element, right? So let's get one more column. So we got 2. So And since these are big now, we can reduce the font size. Okay, so one assignment is 1 goes to 1 and 2 goes to 2, right? And another assignment would be what then? 1 goes to 2 and 2 goes to 1. Okay, just to, yeah, let me just stress here, even though with people like you, this is not really necessary. So this one means what? 1 goes to 1 and 2 goes to 2, right? And this means what? 1 goes to 2 and 2 goes to 1. Now you can see that, and let's call this G to be, let's take another symbol for this. Let's call it a symmetric group on 2 symbols, okay? All right. And well, in one way, this defines the set of symmetries. For example, let's just illustrate this by writing it out. And you can see that this is the identity element. So 1, 2 to 1, no matter which side I multiply, okay, that will be the same. So it is closed here, this type of map. And then also 1, 2 to 1, and then 1, 2 to 1. What will happen here is, if we look at this, and so here 1 goes to 2, 2 goes to 1, so 1 finally goes to 1, and 2 goes to 1, 1 goes to 2, so 2 finally goes to 2. So these are inverses of each other, right? Right, this is inverse of itself rather. And you can see this here. Say we call this 1 and this we call this 2, and we make a line in the middle, and say we just reflect it, then these will just interchange their positions as they did here. And if we don't do anything, it stays like this. So, that's a reason that you can see this is just a set of symmetries of something with only 2 points, all right? Or even this, even if you look at this, if you flip it, it just remains intact, okay? All right, or 1, 2. So that's symmetric with respect to the line in between. Oh, so what I have done is look here. This is a mistake. Actually, I didn't mean that. I meant the identity element multiplied with the other element will give you the other element, and then we have the inverses. Now I'm going to be slow. Boring is better than writing bad statements. Okay. So here, now let's take a set with 3 elements and see what S3 will be. Okay, so one part is simple. I can just, take the identity, right? So 1, 2, 3, 1, 2, 3. Okay, and then I can do this. Now we are looking at different maps. So let's keep one fixed and interchange these two. Okay, and let's make the list bigger. And then I'm going to do this. Let's keep 2 fixed and interchanged 3, right? 3 and 1 with each other. And now we are going to do this. That is, let's leave 3 fixed and interchange these guys, okay? And so we got how many elements? 4 elements in this manner. And then we can do this, let them just all change their places like this. All right. And then let's just let them move further down. So 3, 1, 2, musical chairs with nobody losing. All right, so we have 6 elements. And in this case, we will have 6 elements because it's a 1 onto map. So when you are making a choice for 1, you have 3 choices, right? But for 2, you are now left with 2 choices, right? Because what has happened is 1 has been taken up by 1, and for 3, you are left only with 1 choice. So how many total number of elements we will have here? That is 6. Okay, so we have only 6 elements, and that's what we have described. Okay, and let's again just very briefly visit the symmetries of equilateral triangles. Okay, or the book describes it, but I'll just do it. uh, I'll try to do it very, very fast without making any mistakes. Okay, now I am realizing my limitations that, okay, so let me just go and pull up an app, a very nice app that somebody wrote for us to be able to understand it. Okay, so we are looking at an equilateral triangle, and instead of Desmos, I just brought a GeoGebra app for you, written by Kristen Beck. So we have this equilateral triangle, and what happens is that we are going to look at all the reflections and rotations of this. And there are going to be there are 6 actions here, 1, 2, 3, 4, 5, 6, and that should correspond to the 6 elements that we have. So first we have, say, rotate by 0 degrees, and in that case what will happen is, and first let's just look at our, let's just make a decision here that we will treat the red label as 1, blue label as 2, and yellow label as 3. All right. So in this case, as you know, or as you can see, that we have, if we look at this rotation by 0, it corresponds to identity, right? Because no change. So 1, 2, 3, they stay at 1, 2, 3. Now let's look at the rotation by 120 degrees. So here we are. So what happens in the rotation by 120 degrees? 2 went here, sorry, 1 went here in the place of 2, and 2 went here in the place of 3, and 3 went here in the place of 1. So rotation by 100. So here we have the triangle back in the original position. 1 is here in the lower left corner, then 2, then 3. And if we rotate it by 240 degrees, then in this case, what happens? In this case, we have 3 taking place of 2, 1 taking place of 3, and 2 taking place of 1. That is, the rotation by 240 degrees corresponds to 1, 2, 3 going to 3, 1, 2. So now you can see we have again the triangle in the original position, 1, and this is 2. I moved this 2 up here to avoid the confusion with a square, and we have 3 here. So if we reflect over L1, L1 is this line, then you can see 1 is going to stay unchanged, and 2 and 3 will switch places. As you can see, 2 and 3, they switch places, and we are not going to look at these 2 in here and just directly going to write our results. So for the reflection over L1, what we saw was that if I have 1, 2, 3, 1 stayed fixed and these interchanged places. Over L2, 2 stayed fixed and these switched. And here we have 3 fixed and these 2 interchanged places. Okay. Now, later on, you shall see that an interesting thing is that this portion here that will form a subgroup of S3, because you can check it satisfies the closure property. Let me take that up later. Let's move on to S. So now we got this as a list of elements of S3, that is, these are permutations on three symbols or bijective maps from a set of three elements to three elements. And geometrically we saw just an illustration, that is all these here, okay, all these here, they just show us the rotation of this equilateral triangle. This one is by 120 degrees and this is by 240 degrees, and this is no rotation, or say 360 degrees. It will be all the same. And these all here give us the reflections. For example, this element here, what this does is that if we keep 3 fixed, all right, then I'm just repeating myself, this will reflect the figure through that vertical line. All right, now let's go ahead and use a computer program to help us do stuff faster and do more materials. Okay, so the program that we are going to use is called Sage Math. Okay, and I am very weak in computers and especially programming. I have no ideas. I'll need a lot of help from you. So anyway, if you do this, go to Sage Math. This is open source, doesn't cost you anything. And if you go ahead, then this is the version that I downloaded on my Windows computer and installed it. So you can do the same, or if you have a Mac or Linux, you may do it in a different way. All right. So let me show you how it looks on my Windows computer. Okay. So, I mean, this is the icon that you know, that I click on to get to Sage Math. And once I click on it, it will take me to, to our programming page or whatever you call it. So here we have command prompt, and, I am one of those who finds these kinds of things very intimidating because I almost know nothing about these. I'm just going by whatever I have seen in the guidebooks, and many of them are available free of cost for you, which I shall post for you. So let's look at the symmetric group on three symbols, which is already built in there. So it says, well, it recognized it. And if we want it to show us the elements of that, you can see that here the elements are listed for us. Okay, so the elements that we had, and you can see that the way it has listed the elements looks slightly different. Okay, so let's just go and get used to writing these elements in a different style. Okay, elements of a permutation group in different style. That's what I meant. So I brought them here with the way, we listed the elements. So let's just put some space in here so that we can try to explain and understand them. And I hope that you have reached a level that you might understand it already before I even begin writing. Okay, good. Okay, and let me just embolden them as well. So what happens here is this, that is, when we have, see here, this means, remember this was 0-degree rotation if you recall. So this is identity, and they're showing it as an empty set. Okay, now here for this one, the permutation that they are showing is, or the way this means is, so this is the cycle, that is all these elements are moving cyclically. So this 3 will move to 1. Sorry, yeah, 3 will move under 1. So I get a 3 here. 2 will move under 3. So we have a 2 here. Okay. And 1, sorry. And then 1 is left, and 1 goes under 2 then. Okay. So 3 moves under 1, 2 moves under 3, and 1 moves under 2. Likewise here, well, this is in order, it will be easy. So 2 moves under 1, okay, 3 moves under 2, and then 1 goes ahead and moves under 3. Now here we have only 1, 2, 3 written. That means 1 is fixed. This is 2, 3, and 3 comes down here, and 2 will go here. So they are just moving cyclically. So here there is no 2, means 2 stays under 2, and 3 comes under 1. 1 goes here, and likewise here we have 1, 2, 3. 2 will come under 1, and 3 stays fixed. Okay, so if you look at all these, then this corresponds to this, right? And this one is right here. Okay, and then 1, 2, 2, 1, 1 is fixed, so that one is this one. Okay, and then this is, where is 3, 2, 1? Right here. This goes right here, and this one is here. Okay, so in this way, what happens is, whenever we are given, say we are looking into S4 now, permutation group on 4 symbols, and uh, instead of uh, uh, instead of giving me images like this, somebody just like 2, 3, 1, 4, and with these brackets, this again will mean a cycle. So we have 1, 2, 3, 4. Okay, and here 3 comes under 2, so we have 3. 1 comes under 3, so right here. 4 comes under 1, so 4 goes right here. Okay, and then we have, excuse me, so then we have 1 and 2 comes under 4. Okay, so that's what this permutation means here. Okay, so in this way, what we have is, let's just go over some more terminologies. Now first, let us quickly see that how we multiply permutations. So I'm taking permutations alpha and beta in S5. That means the permutation group of all the bijective maps or 1-1 onto maps on 5 symbols, that is, say 1, 2, 3, 4, 5. So alpha is given by this. That means 1 goes to 2, or alpha of 1 is 2, 2 goes to 3, alpha of 2 is 3, then alpha of 3 is 5, alpha of 4 is 4, and alpha of 5 is 1. Likewise for betas, what we have is, so here 1 goes to 4, so beta of 1 is 4, like beta of 2 is 3, etc., etc., right? Now say we are doing this, multiplying these two permutations, okay? And so that means we have this, which means what? We have alpha times beta, and basically, if you remember, we have this as composition of maps, right? So what we have is, let's just put the composition symbol in between. That is, where did the composition symbol go? Right here. Okay, so that means we are going to take the composition of beta with alpha, and the way the book does is we will go the same order, and that's how we did the composition of maps. We will apply beta first. So what this will be 1, 2, 3, 4, 5, and under 1 we will have what? Beta composed with alpha of 1, and we will just proceed in that manner. So let's just write these down. This would be what? This would be alpha of beta of 1, right? Oh, sorry. Alpha of beta of 1, right? So here alpha, then we will write beta of 1, and that gives me what? That gives me, if you look at beta of 1 is 4, okay, and alpha of 4 is how much? 4, right? Okay, so going in that style, what we have is that under beta composed with alpha, 1 will go to 4. Let's see what will happen to 2. Okay, so we will go for 2 now. So here 2, so we will have alpha of beta of 2 very quickly. You must have read it by now. 2 goes to 3. So this is 3. And alpha of 3 is how much? That's a 5. Okay. And then likewise, we can go for this composition with 3. So we got beta of 3 is how much? Beta of 3 is 2. So we are writing alpha of 2, which happens to be 3. So under this composition, what you have is that you got, excuse me, that you got 3 going to 3. Okay. And then here we got 4 here. So beta of 4 is how much? Beta of 4 is 5, and alpha of 5 is 1, right? Our alpha of 5 is 1. So 4 goes to 1, and then we have just one more left. We can write it quickly. Okay, so we got this here. So we are writing that of 5. Okay, so here we have beta of 5, and beta of 5 is how much? That's 1, and alpha of 1 is how much? Alpha of 1 is 2, right? So if we write this composition, right? Okay, then what we have is, let me just write a new one. I will not copy paste this time. Okay, so here we got this. So in the first row we have 1, 2, 3, 4, 5, and in the second row what we are going to write? We are going to write the images of these as what? Under alpha O, under beta composed with alpha. So what we will have? We have 4 for 2, 2 lands at 5. So we got 5. 3 stays there. 3 eventually goes to 3. 4 goes to 1, right? And 5 goes where to? 2. So this product equals how much? This product simply equals this permutation, right? Now let's just quickly compare our answer with the answer in Sage. Okay, and remember, for Sage, Sage will write this as this Sage math I'm talking about, right? So we will have this, and then we want to multiply that with, what it does is just writes the second row, because they are, the approximate images of the first row. So this product should be in the Sage symbols. Okay, 4, 5, 3, 1, 2. So what we will do now is we will look at Sage and see if we have no, if our answer agrees with theirs, and theirs will more likely be right, so we will check, okay? So here we are going to compare our answer with Sage. So this is the permutation alpha, let's call it A. And the way Sage will write it as that 1, 2, 3, 4, 5 assumed to be in order. Then 2, 3, 5, 4, 1 are their images in order. So we entered this. Okay, and then for B, what we will do is B is which permutation? Right here, this one. So there we shall write 4, 3, 2, 5, 1. So now we got our B in here. Okay. So now what we are going to do is we are going to multiply B. Okay. And I want write action via product. Okay. So product with A. Okay. And once we do that, we can see we get the same product 4 5 3 1 2. So here we have 4 5 3 1 2, and if we do it the other way around, that is say we did this, that is excuse me, that is brought this here, okay, and change, and we change A to B, all right, and then B to A. So this will be the product other way around, okay. So A, and then we shall see if it agrees with our way of multiplying. Of course, it's multiplying it the same way. So what we got here is we got 32154. So let's take that into our document. So here we saw that if we multiply, this is our A, this is B, okay, and if we multiply AB, we got this as our images, which was this. Now let's look in this case. So you can see 1 goes to 2, 2 goes to 3. So we will have 3 here, 2 to 3, 3 to 2. So we shall have 2 here, 3 to 5, 5 to 1. So we got a 1, 4 to 4, 4 to 5. We got 5 here. Okay, and 4 is the only one left for here. And you got 3, 2, 1, 5, 4, okay, as a sequence in the images, and that's the other way around. Now we shall have just, shorter symbols for multiplying, but here, since we wanted to stay in the style with the book, that's why we wrote all that out. Okay, so anyways, that's how you will multiply permutations, as exactly as you take the composition of maps. Okay. Now let us consider this permutation in S5. Okay, and we are just going to write it in a different way, or we are going to write this as a cycle. Remember, I'm going to review cycles for you, and then we shall write it as a product of disjoint cycles later. So first notice this. These guys here, they don't move, right? So we will not list them in our permutation now. And so when they are not listed, that means that they are not moving, right? So the only moving objects in here are 1, 4, and 5. And then what we got? We got 5, and then we got 1, and then we got 4. Okay, now let's write them in a slightly different manner. Okay, so we are going to write this as a cycle, as we saw before. So the way we will write is that first we have 1, and then 1 goes to 5. Let's write 5 next. Okay, then 5 goes to 4, then we write 4. So it shows that these three elements, or these three values, they move cyclically. 1 goes to 5, 5 goes to 4, and 4 goes to 1, as we saw in a display in comparison with the listed values in Sage Math and that of the group of symmetries. Okay, so let's just review it once again. We'll take a minute. So what we have is that if we have, say, 1, 5, 4, that's a cycle, and it's called a 3 cycle because there are 3 distinct symbols in here. So that's called the length of the cycle. So we have 1, 5, 4, and we are moving them cyclically. 5, 4, 1 goes here, that's the 1. And if we want to realize this as an element of S5, then we will insert 2, 4, just write, 2, 3, just write that they are the same, they don't move. And here it's just a regular looking element of S5. Okay, so we saw that we have a cycle, and we also saw we can multiply permutations and they don't generally commute, right? So let's practice that with one more element in S5 where we got this one. So you can see, let's write it like this. We start with a 1, right? And then 1 goes to where? 5. So we'll write 5 the way we wrote before. And then 5 goes to 2, and 2 comes back to 1. So this part is complete. So this just goes ahead and describes this portion for us. And then we will start with 2. 2 goes to where? Oh, no, sorry, not 2. I apologize. 2 is already there. Let's say 3. 3 goes to 4. So we'll write a 4 here. And 4 is back to 3. So these guys are accounted for. So you can see that we wrote this as a product of disjoint cycles. Disjoint because they have nothing in common, right? Okay, this and this, they don't have any symbols in common. And you can see that the length of this cycle is 3 and length of this cycle is 2. And at the same time, notice this, that if we have disjoint cycles, then we see that they commute, and that is true in general. So the book has proven many theorems for us, and I'm going to list them all, okay, that we will be using. So what we just got is this, that every permutation, okay, can be written as a product of disjoint cycles. Okay, so, and the result is proved in the book. I'm not going to go over the proof again because we have already exhausted a lot of time, and we just need to do a few more things. Okay, so here are 2 theorems that we have used so far, that any permutation can be written as a product of disjoint cycles, and 2 disjoint cycles commute. That is, if we interchange their places, the outcome will be the same. And we are using this free textbook, Abstract Algebra, Theory and Applications by Judson. So here we are going to use our free computer program, okay, to break a given permutation into disjoint cycles, and we are going to write this same permutation. And remember, the way Sage Math will take it is that we will just write a sequence of the images, the sequence in which they occur for typical 1, 2, 3, 4, 5, and then we want to do what? We want to decompose this into a product of cycles. Okay, so this is the command in here, and once we do that, you can see we got the same thing, 1, 5, 2 times 3, 4. So that's the output. And with the when it says parentheses, that means it means cycles. All right. When we have a cycle of length 2, we call it a transposition. So for example, this cycle 3, 4 is a transposition. And now we can see that every cycle can be written as a product of transpositions. Okay, it may not be unique. Okay, that I will leave for you as an exercise. Okay, but you can express any cycle as a product of transpositions, and the method is very simple. For instance, say we take this cycle 1, 5, 2. All right. Now this is already a transposition. So for this one, what we can do is that we have okay, we'll write a 1, and let's start from the right because that's how we multiply. So we'll write 1, 2, and then we shall write 1 and then the next element on the left. Now, if you want, you can just go ahead and verify that if you multiply these two, see what you get. And this is just an illustration, this is not a proof. The book does a good job of doing this proof for you. Okay, so we have 1, 2, 3. All right. So here 1 goes to 5 and 5 stays at 5. So that's 5. Now then 2 goes to 2. Here 2 goes to 1. So we have a 1. 3 here goes to 3. All right. And I don't know why I wrote a 3 here because 3 goes to 3. So that would not be there. That should have been a 5. 3 and 4 are suppressed because in this particular cycle, they don't move, right? So 2 goes to 1 and then 5 goes to 2. Or if you want, you can just go back to this notation. That is, here we have, we can start at 1. 1 goes to 5. So we can write a 5 here. Then 2 is left. So you can see this product is the same as this cycle. So every cycle can be written as a product of transposition, and consequently every permutation, okay, may be expressed as a product of transpositions. Okay, and now oh, now the number of factors in a product of transpositions that we use to express it may be even or it may be odd, but it cannot be both. So the if the number of transpositions, okay, or just a second, if an expression as a product of transpositions, okay, for a permutation is even, okay, we call the permutation an even permutation. Okay, and again, as I said, the number of factors can either be even or odd, but not both. We call this permutation an even permutation. Otherwise, it is an odd permutation. Okay. Permutation. Okay. Now, just one last thing. that is the subset of even permutations of Sn is a subgroup, okay? And that should be, so is a subgroup of Sn because, remember this, if I have a finite group, then in order to be a subgroup, all I need to have is satisfy the closure property. And your book proves that identity is an even permutation. So you can see we are talking about a non-empty subset. So here, um, you can see this here, product of two even permutations is even. Why? Because when the factorization is even for two, even plus even would be the total factorization of the product. That will again be even. Okay, so product of two even permutations is even. Therefore, the subset of even permutations is closed, all right. Therefore, is a subgroup. Okay, so there is a name for this subgroup. So the subgroup of even permutations of a symmetric group Sn is known as, okay, is called the alternating group on n symbols, okay, and we denote it by simply a sub n, okay. All right. So, well, I think that there were too many terminologies in here. So let me stop this particular presentation. And what I will do is that I shall take more of an, okay, in a different context that we will be doing. Let's break the monotony by looking at some other things, and we will discuss this an more in detail in the subsequent presentations. Okay. All right.